and automation project and is the founder of technology service company Harman.
Shall we start? Okay. Thank you everyone for attending last talk of the day. So everyone's probably this thing. I'm lucky that there was one talk before this, so everyone got to sleep off their lunch. But this is going to be it. So this is a talk about CFFI mainly, and how you can use this to test programs that are written in languages, lower level languages like C and all of that. Right, so this is slightly intermediate. You should be familiar with C a little bit. So we'll try to cover things as we go along. So by way of introduction, he already introduced me, but this is just something about myself. I have a small company which is a services firm which basically does infrastructure automation kind of work. Right, I'm also a co-founder of People Academy, where we do niche trainings, Python, Git, specialized areas in Python, etc. I also mentor students, so via Lyceum, which is like a mentoring setup which I've done. But like he said, I've been involved with PyCon India since the early days, and that's my Twitter handle. So if you want to stay in touch and things like that. All right, so this talk is going to be the outline. I'm going to introduce the ideas a little bit. I'm going to talk about FFI. I'll tell you what that is right in a while. Then I'll talk about how to test libraries using this, and then some extras if we have time. So first thing, like coupling between languages. The thing is, like a lot of people talked about setups where the whole thing is distributed with microservices and things like that. In situations like this, we often implement different parts of our system in different languages. Like one part's written in Python because we want it to be quickly changing. The other part is written in something like C because we want to interface it with hardware. The other part is written in something else because for whatever reason. And we need a way to actually communicate between these various pieces. Right? So the one which most people will be familiar with is web-based APIs. So you make a REST call, right, or an RPC call or something. And this thing, it goes via HTTP, and service runs, produces some output, returns it back. All right? This is extremely flexible because these two services, they need not be on the same machine, they need not be in the same geography, they need not run on similar hardware. It's completely, very loosely coupled. But there are some downsides. Specifically, there's issues with serialization of data. Like you have to send this thing out in some format which HTTP can handle properly. There's also issues with speed. It's not exactly fast doing this. Right? So a slightly more coupled version would be IPC, that's inter-process communication on a single machine. So suppose if you used Unix, then you've seen Unix pipes, like the pipe thing. So when you do that, like output of the two programs can communicate via a pipe. And that is another way of having multiple programs, using the services of one program in another. There are also ways of doing it using named sockets, shared memory, things like that. This is faster. It's also a bit, it's on the same system. It has some limitations because things have to be on the same system, etc. But it is faster. Even better is if you have a common runtime. So like finally these two languages which you have written, they finally compile down to a common runtime. So you have lots of languages written on the JVM, for example. So if you have something written in Java proper and you have something written in Clojure or something else, at one level they're the same, right? So you can actually use things from one in the other. Now you get up to that level, and now just imagine that you don't have the runtime at all. The runtime is the actual machine itself. That's when you have FFI. FFI stands for Foreign Function Interface. So the idea is that you can actually call a compiled low-level function from a higher-level language directly. You pass control to that. It does this thing and returns it back, returns you the response back. This is called FFI. Okay. This allows you to actually leverage, like modules that are written at system level. So like your libc, for example, your low-level C libraries, or some low-level library which is written in a low-level language like C or even assembly or something. And you can actually call those functions directly from within Python. Okay. So many languages have this. I think in Java it's called JNI. With this thing, there are others. So have any of you, okay, so as an aside related to this, so there's this distinction between language warriors, which are people who like I'm a Python guy, I'm a Ruby guy, etc. And then there's the languages themselves, Python and Ruby. So usually the languages don't have a problem cooperating. Right? So if there's a Clojure program has no issues calling a Java function, but a Clojure programmer has a serious problem calling a Java function. Right? So it's not really the languages or the technologies, it's stuck-up programmers. Right? So probably there's some lesson to be learned from this. I don't know. I'm just throwing it out there. So come back to the thing. So this talk specifically is about, I've been working on this library called cpslib, on and off. It's basically just to sharpen my C. If anyone wants to contribute, you're welcome. It's a simple library for getting information about your system, like number of CPUs, how much memory you have, and what disk utilization, packets on your network, things like that, and in a cross-platform fashion. So right now it works on Linux and Mac OS. We're working on the Windows bits. The thing is, like, this is actually a port of a library from Unix, from Python called psutil. Have you used psutil? At least some people must have used psutil. So this is actually a port of that into C. So I have something to test against. I want this thing to be equal to psutil. But psutil is fully written in C. I mean, fully written in Python, mostly written in Python. And the other problem with psutil is, like, it's not, the system parts and the Python parts are not clearly separate. So it's like a mix. It's like the whole thing works, but there are no pieces inside that you can decouple and take out. So the only way to run psutil is from within Python itself. Right? So I needed some way to test my library against psutil, and that's how this whole thing came up. So I'm going to use Python to actually write tests for my C library, and then compare them with psutil. That's the basic intention. Yeah, so here's a quick quick look at example cpslib function. So simple things like here you can see that we have something here like CPU count. It'll return you a number of logical and physical CPUs. Right? So here, so this, if you pass false, it returns the number of physical CPUs. So you say physical CPU count, you pass false, it tells you how many CPUs there are. So I compile this program with pslib, and then I call it, it tells me there's one physical CPU. Does this make sense? This is C, so I mean, if you're not familiar with C, but this is C. So it just calls this function. This is an example of a function. The function is actually implemented somewhere else. I'm just linking the library directly over here. So this is the way I would use it if I were writing a complete C program. All right. I'll send out links to all this code and the presentation and all that, so you can look it up and find bugs and annoy me. But this is the basic gist of it. So this is what it is. Now I need to actually run this from within Python so that I can compare it with psutil. The problem is there's no real clean way to do that. One way is to actually write shell, small C programs that will just call these functions and then subprocess and call them and then read std out and that. But that's not very nice, and there's not much learning to be done that way. So I started exploring this. So there's a part of the standard library called Ctypes. Has anyone here used it? Some people might have used it. So Ctypes is like an FFI library that's part of Python itself. It's in the standard library. So if you want to use this, here's how you would use it. So you just, in this case, I'm simplifying here. You import Ctypes. You say cdll. You pass the SO, the shared object which you compile. You load it up like this. And then you directly call functions inside that. CPU count, you can pass true, you can pass false. So you pass true, it returns 4 virtual CPUs. This thing is physical CPUs. Right? So this works. Okay, so this is simplifying because this is a very simple function. It takes like a Boolean and returns an integer, so it's okay. For complex types like structures and things like that, it can get a little more hairy. So I have one example, which we'll use as an example throughout the thing. All right, the example is a somewhat infamous function, Leftpad. So people who read Hacker News and all will be familiar with Leftpad. It's been in the news recently. So I have a C implementation of Leftpad because, as we know, Leftpad is like internet infrastructure, right? It's very important. So it has to be implemented in the kernel or something. It has to be fast. So we have a C implementation of Leftpad. It takes a character buffer, the size of the input, and it tells you how much you want to pad it by the size of the output. And you compile this into a lib-leftpad.so. Okay, so this is the thing to compile. This is just, I'm not written the implementation, that's there in the code. That's there on the website. You don't have to, I'm not putting it on the slide. So you compile that, you get a lib-leftpad.so. And you load it up here, leftpad equal to cdll lib-leftpad.so. And you can see that it takes three things. It takes char star, character array, size t, that's for the number of bytes here, size t again for number of things you want in the final output, and returns a char star, a new thing. I have to specify these input and output types, okay, for Ctypes to work. So you say leftpad.leftpad string, that's the name of the function. Arg types is ccarp, csize t, and the return type is ccarp. You do this, then you can call it. If you say IP equal to, you get lib leftpad. So I've written a function called leftpad that's going to wrap this leftpad string. You get an input, which is a string. You have to encode it as ASCII. Why do you have to encode it as ASCII? Because we are using Python 3. Right? Is anybody using Python 2? Okay, if anyone's using Python 2, write your names on a piece of paper. We'll deal with you later. So Python 2 is going to die within 1,000 days. I think 1,000 days was like, I read that a few days ago, so less than 1,000 days. Right, that's end of life for Python 2. So if you have not moved to Python 3 yet, where have you been? Okay, so move fast. So Python, see, so the thing is like, it's when you do cross-language things that these things become apparent. Python 2 strings are, they're really byte arrays, but you sort of treat them as strings, and then you have Unicode that's something else. It's vague. But here it's not, right? Python 3, you say input is, I get it as a string. I encode it as ASCII, so it's like 8 bits. Each thing is a byte. I encode that. I pass this to this. So IP becomes char star. The length of that becomes this, and I pad it to 20. So it gets this, and then you return this. Red code, you decode it as ASCII. So you get back a byte string. You decode that as ASCII, and you get it back. So here, if I give python, I get back Python with padded to 20 spaces, left padded. This works. So this is actually working, the actual work of left padding, which is done in C for performance reasons. Okay, so leftpad.so is the one who actually does the work. This is actually quite nice because and of course, like since I mentioned Python 3, like the first question people will ask me is like, why are you using %s here? Shouldn't you be using open brace, close brace? And the reason is because this thing actually works with Python. Okay, this works with Python 3. It works with PyPy, which is at 2.7. something. This thing also works with Jython. Okay, this same code will work with Jython. If you run Jython with this, you will get back this Python. It uses, I guess, JNI to do it internally. So, but Jython is stuck in 2. something. So if you put the braces thing, it won't work with Jython. That's why I put this. So this program will run with all 3 interpreters. Okay, if you don't believe me, I'll show it to you after the presentation. Yeah. So Ctypes, it works with PyPy, CPython, and even Jython. Anyone use Jython in production? You know anybody who uses Jython in production? I think I know one guy, but it's not well. So this is really nice. Ctypes, it does all this. Then why CFFI? Why is there another FFI library for Python? That's the question. So my talk is specifically about CFFI. I use Ctypes just as a vehicle to get you familiar with what FFI is. So CFFI has a bunch of advantages. One is it does not have a DSL for types. It doesn't have the C size T, ccarp, etc. Okay. For complex declarations, like you have the input is a structure with like a character array and another array of structures, a pointer to this. You have to write this whole thing in a DSL, pretty much, to tell Ctypes that this is what my function expects. Okay. If you don't write this properly, it's not that you will get an exception. Your interpreter will segfault. Okay. So being Python programmers, you're used to things, raising exceptions and being under control. But once you pass control to C, then it's like BG mentioned, like, programming languages give you a fake idea of the universe. So once you go down to C level, it doesn't do all this. Like, crash, proper crash. Okay, so it doesn't really hide you from the details. So you can segfault your interpreter and all if you write these things wrongly. So the main advantage CFFI has is it doesn't have a DSL. That's one thing. I'll show you how it works. Second thing is it can work at API or ABI level. This is interesting. So this thing which we just saw, the Ctypes thing, works at the ABI level. What is ABI? Yeah, I mean, of course. But the thing is, the idea is like, it's like, you know, the conventions of how this thing is called, okay, at the system level. So it basically deals with issues like how structures are packed into memory, where these where the data should be put when control is passed to the other function, things like that. And these things are not really portable. Like the way you do it on Windows might be different from the way you do it on this. If it was compiled with one compiler and your FFI library was compiled with some other thing or with some other different compiler flags, this might break. Okay, so ABI is not portable. It works, but it's not as portable as API. Okay, but with Ctypes, you don't have an API option. You only have an ABI option. CFFI, on the other hand, can work with ABI or API. So I'll show you both as examples. You'll understand what that means. So API is more portable, but the problem is you need a C compiler. ABI is less portable, but you can just download and start using it if you have the SO from your package manager or wherever. Okay, it's also faster, so I'll show you that also. So here's an example of the same thing, but using CFFI with ABI. Okay, so it's similar to Ctypes. You can see it. We import CFFI, the CFFI.FFI. Instead of typing that, you know, like argtypes equal to crt, size tp, whatever, you cut paste the declaration directly over here. It will actually parse the C code and figure out all this. It uses PyC parser or something inside, all right, which is very neat. Like you have one source of truth now, your header file, right? If you want to access library functions in the C standard library, you can actually cut paste from the man page, okay, and just say cdef that, it'll work, right? So you cut paste that here. This function, this line basically tells it that leftpad string is a function that takes these things as input, returns this as output, etc. Then I open the leftpad thing. I say the same thing, then ip.encode this, cleftpad, it's called cleftpad here. cleftpad.leftpad string, I pass all this stuff, I decode the output to this. This ffi.string is basically like your Python str. Okay. So this gets it out and you return it back. So it's similar to Ctypes. Okay, so it works with this, and this thing actually makes a lot of headache easy. Like I don't know if you've done any X Windows programming. Like X Windows programming, yeah, you had a question? Yeah, you can include that. I'll come to that. I mean, my library uses a bunch of other things. I'll come to that. So I don't know if you've done any X programming, but you have things like, there's a function there called xCreateWindow. It has like 13 or 14 things you need, color depth, display, and a bunch of other things. I guess it was complicated, so they made xCreateSimpleWindow, which takes 11 parameters. Okay, so even that is a bit hard. So this kind of thing makes that easy. You can just cut paste your stuff here. This works, but the problem is this is ABI. Okay, so like for example, like if you're using Ctypes and you call a function with improper parameters and things like that, it'll crash. On Linux, it'll crash. On Windows, it won't crash, but it gives you an exception saying type error or something. But how it does it is, it first calls the function, does all the damage. After that, it inspects the call stack to figure out that this thing was not properly returned, wraps that as an exception and gives it to you. Okay, which is not only like, you know, it's not only a lie, it's a dangerous lie. Because you expect an exception, you expect exceptions before the damage is done, but that's not the case here, right? So ABI, there are several issues like that. So the only guy who really knows how this packing and all is properly done is the compiler. So how do we do that? We use the API method. When you use the API thing, what you can do is you say FFI dot. With the API thing, you need a build script. You have to first build the C extension, and then you can use it. I mentioned that you need the compiler to use the API. So you do it like this. You say import FFI. You say set source. Okay, you say I want a module called pyleftpad. This empty string over here, you can put extra hash includes or type defs or whatever. So that's basically where you put stuff. So you say libraries, it uses lib leftpad. So this is basically -L that. And dir, so this -L for dot current directory. And then you put the same cdef over here. And then you say ffi.compile. If you do this, what happens is it generates a C file, it compiles it, and creates pyleftpad.so. Okay. So it gives you a native C extension, okay, which is really cool. No more manual C extensions. You don't have to do all that tedious boilerplate.c business, py void and pyint and py all that shit. You just do this, it creates this thing for you. Not only that, the C file it creates can, if you compile this thing with CPython, you get a CPython extension. You compile it with PyPy, you get a thing you can import in PyPy, which is really nice. So you get that. So this. Okay, and then only one thing you should understand is that this exposes function by function. So you probably want a higher level wrapper on top, which puts these things inside a class, etc. But basically, it does the wrapping for you. Okay. So once you do that, you can just import pyleftpad. You can load it up, and you can do the rest of this pyleftpad. It has a .lib to get the thing, and then leftpad string. You put this thing, and pyleftpad.ffi for the string thing. You decode. You get the same thing. Okay, this is the compiled version. Only thing is you have to run that other script once, the build script once. Here's some timing numbers. So this is Ctypes. With CFFI API gives you this, CFFI ABI gives you this, Ctypes gives you this. CFFI API obviously is fastest because it's like completely compiled, right? The compile time thing, it's statically typed, etc. So how do you do this now when we are doing it for our libraries? The general thing is to set source for headers, cdef for all declarations. So set source, the thing which I mentioned over here, set source. This thing allows you to put all your hash includes and all those other things. You set source for everything you need. You cdef all the declarations that you want. You build a native extension, you load it up, and then you start using it as if it were pure Python. So if we wanted to actually test our leftpad thing, you would say from leftpad CFFI API import leftpad, and you'd say test leftpad, IP is equal to Python, assert leftpad IP equal to IPR just 20. This is a test for the leftpad function. Okay, I don't know, like leftpad actually had a lot of tests and all that, the original leftpad. So yes, yeah. So and this can run using py.test. It's all the rest of the Python testing ecosystem you get, which is very nice. So we had the library which I was working on was called cpslib, and this is the build script for that. It's not as clean as it should be. Contributions welcome. But basically, what it does is we include all the stuff over here. Instead of getting all the declarations manually, we just open the header file, get rid of the hash includes, and put everything else inside this. Okay, so the header file contains everything. I don't have to retype all that. And then you compile it. This gives us cpslib. There's some issues with what can come here and what can come here. So there's some open bugs with CFFI about this. So that's some vagueness is there, but basically you can do it. And then you get it like this. So this was our CPU test. So I get psutil, I get pycslib, import this as this. So test logical CPUs would be my CPU count and psutil's CPU count. Whereas this one would be my physical count and psutil's physical count. Right? This actually allows me to test my C library against a Python library using Python tests written in Python. Right? So you can do -x, minus pdb, blah, blah, all that stuff, which is very nice. It's very convenient. Okay. Now, there's one thing extra which I'd like to mention, which is test coverage. So you have for C libraries, you have gcov. Okay, gcov it's a C tool, which is not really it's not as easy as pip install pytest coverage --cov. It's not like that. What you do is you have to compile your library with a few extra flags, basically your fprofile args, ftest coverage. If you do that, you get a gcno file, which is the call graph of your thing. After that, you run your leftpad script. In this case, we'll be running tests, not the script. You're running leftpad script, you'll get a gcda file, which is the actual coverage data. Okay, but it's not in human readable format because that would be too easy. Then you run gcov leftpad. Okay, that will interpret the file. Okay, but that won't print it to the screen because that would be too easy. It would write it into a file called leftpad.c.gcov. Okay. You open that, you'll get it. But it's useful. It's very useful. If you're doing low-level stuff, it's very, very useful. I'm not dissing it. I'm just saying there's a lot of things to do, especially when you're coming from Python. So I wrote something called pytest-gcov that automates this for you. So you just run your tests. At the end, you'll get a summary of this much coverage, etc. It's buggy, it's flaky, but it works for me. Okay, so it's a starting point. Basically, there's a thing called gcov flush, which flushes the data out onto disk after the test is done. Unfortunately, there is no way to manually call that, except when the program dies, it gets called automatically by the instrumentation code. So I FFI'd to that and tried calling it, but then the library has to call it. Python py.test calling it is not enough. Okay, so there's this, but it works. Okay, so I get coverage data. So that's basically the thing. So yeah, so that's basically my talk. I'm leaving it for questions now because it's more based on that. Yeah. Yeah, because once it's written in Python, it doesn't make a difference, right?
Right, but any specific reason why you didn't inherit from that unit test.me? Nothing
I
like
use
that,
py.test.
right?
Py.test, you just say
Cool.
test underscore.
Okay, nothing special about
No.
py.test.
So py.test is my, like, why should you use Python? Py.test and SQL Alchemy. Those are my killer libraries for Python. I'm a big fan. But you can do that also. No import unit, subclass, all that stuff. That's fine. It'll work. Anything else? Yeah.
How does Cython fit into this? I mean,
So Cython is like you basically annotate the code. I haven't used it. Like I tried to use it once to wrap some USB C library once, but I got really confused and I ended up writing a C thing natively. I think you annotate functions with types and then it produces a C file and you compile it. It didn't work for me. Okay. I don't know. Maybe I was just too stupid for it. But I got it working faster by writing raw C. But then this thing takes the headache out of that because I just want to expose these functions as these libraries. That's it. There's no more logic as such in the wrapper. Okay. So I write the C code here. The wrapper is auto-generated. I write the Python code myself. So nice that way. I don't have to spend time on writing the wrapper manually. Basically, the C wrapper is what? It's basically translating types. Right? You get an int here, you convert it into C int, you unbox it, get all the data out, you put it back and send it back. That's what you do. But that can be done automatically.
for coverage, did you look at LCOV? LCOV, it's a front end for GCC, which basically makes your life easier.
Oh, okay, I should look at that. LCOV, is it?
Yes.
I'll look at that. Yeah, this.
How good is this when you're using callback functions in your C library?
I haven't tried it. So my thing doesn't, right now there's no, so the headache is, yeah, I mean, if your callback is written in Python, is that what you're saying?
Yeah, so your C library is using callback functions. So now you have to
pass that from somewhere.
Write a Python function which should be
yeah,
invoked
I haven't
from
tried.
C.
I don't know.
Any more questions?
All right, so I'm available if you want to talk about it. Thank you.